some of the work we've been doing on development of a crypto framework for DPDK. I'm part of the development team in Shannon. So really when we kicked off this project, the scope of the work, we wanted to design a crypto framework that was going to work with the standard model that we use within DPDK, the burst-oriented APIs that accept MBUFs. We wanted a framework and a way of actually creating with crypto offloads that were going to be independent of the underlying PMD implementation. So we wanted the same APIs to be usable from if you're going to be using something like the Intel's QuickSys hardware underlying, or if you're doing on-core, maybe using the other implementation that we have is based on the ASNI multi-buffer library that's been developed by one of Intel's security teams. We want also obviously to support chaining of crypto operations, so you can use one operation to do both the cipher and hash transforms in a single request. And also we looked at adding both session-based and sessionless crypto operations. So yeah, I'll explain that a little bit more further on. So as I said, fundamentally it's a burst-oriented API. And it looks like the main APIs were actually enqueuing data to a crypto device, look very much like an ETH device. You've got instead of an RX and TX, you've got an enqueue burst, so that's loading, putting the work out to the crypto device to get processed, and then asynchronously you can then call the DQ at the other side. So to achieve this, you're passing in the arrays of MBUFs. So I had to add a new pointer into the MBUF to allow us to pass the crypto operation details, and then use an offload flag that gets set in the MBUF. So when you push a burst into a packet, each packet to get processed needs to have a valid crypto operation structure attached to the MBUF. So these are the basic crypto primitives. So if you've used OCF and BSD, or I suppose even if you're familiar with using the QuickSys APIs as exist for the current hardware, or even these are all the basic things that are quite similar even to ODP's crypto APIs. They're the basic definitions of different cipher and authentication algorithms, and then the operations that you want to perform. Nothing too exciting about those. And then this is actually new. This has changed since the actual RFC that went onto the mailing list a few weeks, or probably about 2 months ago now. This is it's to allow a greater flexibility in how when you're creating sessions, or when you want to actually describe what sort of crypto transformations you want to be provided. What you do is you create a chain of the crypto operations. So each what I call a crypto transform. So each transform has a pointer to the next one. So if it's possible for a hardware device to possibly support 3 or 4 transforms in a single operation, you would have 4 transform structures defining the transform type. And then, so in this case, we only currently have obviously a cipher and an authentication transform type. So the normal operation would be you would have 2 transforms chained together. And then I've just, under the lower details here, I've just shown what the underlying transforms for cipher and authentication would look like. So you're setting the operation, the algorithm, and then providing the key. So this is the structure that would be if you're creating sessions. So if you want to, the standard way of doing crypto operations is for, say, a flow of data, you're going to have a standard crypto operation, or standard definition of what you want to do to that flow. So it's it's going to be the same encryption, same authentication details for every packet in that flow. But for that immutable data, you don't want to be doing the cipher key expansions, and for the authentication, you don't want to be doing the iPad and OPAD calculations for every time you're doing the packet. Obviously, the way it's done in all of the crypto frameworks that exist, you do those up front. You have that information cached, and then you attach that to your crypto operation. So just a little bit later on, I'll show you visually how these things link together, but this is in general the immutable data. So then we've got the crypto session create, and that's passing you do chain of transformations, and then you do that in a crypto ID. So the one current limitation at the moment, if you're working with sessions, a session is created for the underlying device, because if you want to create that in the most the efficient way, you have to use, so if it's a PMD, it's a hardware PMD, you may have ending issues that you have to want to have the keys in the correct endingness. So crypto sessions are currently, if you have multiple devices of the same type, you can use that session created on any device with that device type. But at the moment, we're limited that if you create a session with a software crypto PMD, you can't use that on the hardware PMD, because it'll give you a unsupported crypto session failure at that point. So I'm looking at ways as we proceed with this to make that more flexible, that possibly that we'd be able to create, if you ran into that situation, that you may be able to create, the first time you hit software, if you've only had a session before used on hardware, that you would then create that software cached session, and then you could use that from that point forward. To improve efficiency of that, we have session pools that are managed within the crypto device framework, and they provide some hooks back to the actual implementation of PMD. So you can, inside the PMD, if you want for things like cleaning up the keys after a session's finished, you can define exactly what elements of the session you need to erase after the usage, and also you can tell the framework obviously the size, the amount of private data you require to handle all of your key material. So then I'm just saying again, the sessions are linked to a particular type of crypto device. So the crypto operation, this is the structure that gets attached and filled out. It's on a packet per packet basis. So this is the immutable data that's changing from packet to packet. So your offsets into the mbuff and the length of the data, and it also contains things like the pointers to IV digests and additional authentication data as they're required for the particular transform. So those parameters, IV digest, they could be pointed internally within the mbuffs. More common if you're looking at something like IPsec and an ingress path, or you could have those allocated in another location. The only limitation being if you're using a hardware device, those need to be in physically addressable space. So the next slide here. So this is kind of just a diagram showing how it fits together. So you've got your standard mbuff with your payload and headroom. You might have the IV data and digest coming in if you were doing handling ingress traffic, some IPsec. So you're going to attach. So I suppose I guess in a use case such as IPsec, you're going to have done a lookup on the IPs and your SPI, etc. So you find your session, you match your session, and then you fill out the different parameters within the crypto op. So the crypto operation is pointing to where the IV is in the digest, and it has the offsets and lengths. And then you've also attached to that the pointer to the session, so that that's the session data, which is defining the key, which has the keys and defines the actual operation that's going to take place on the payload of the mbuff. So we've created operation pools, so they're very much in the same image as the packet mbuff pools. So as you're going to be creating these, using these on a packet per packet basis, we've got a pre-allocated pool up front that you can pull from just to speed along this, and then just the standard. These are just showing standard APIs that we have for creating a pool and allocating operations from the pool, and then you can then free it up when you've finished processing in the crypto device. One thing to notice here, this is just relating to our session. Using the sessionless API. I've got support here for, you can set a number of X forms. So if you're doing a sessionless based processing, this allows you to say, I may want to use, I want to use two transforms. I'm going to use two transforms in my sessionless operation. So you don't have a pre-allocated session, and you just fill in those X forms, and they're included in the crypto operation. So that means that you don't have to do all the mallocating of memory for those as you go. And so yeah, so this is the there is actually then when you're using, this is from this, it will be from the same mempool, but we use a separate sessionless alloc function, which then defines the number of transforms that it, and it's just appended. Actually, I'll show you in this diagram. I'm just showing here the grey in the crypto op. So if you were to want to use the sessionless APIs, that memory would be allocated at the end of the crypto op structure. So then you're just filling out the parameters there. And so then on each transform, you select the type of transform, and the next pointers will be already allocated, will be already be set up when you call the sessionless API. And then I suppose the one disadvantage of using the sessionless is when you actually submit the job to the device, you need to do the expansion of the crypto keys in line with the actual operation and processing. But it gives a certain level of flexibility if you're dealing with lots of once-off type traffic. So implemented PMDs that we've done, we've got 2 PMDs with the patch set that's on, currently the V1 that's on DPDK. We've one based around the SNI multi-buffer library that was developed by the Intel security team, and it takes advantage of the SNI instruction sets on core that accelerate the AES encryption and decryption. So the PMD is basically a lightweight wrapper around the multi-buffer library. It also makes very strong use of the vectorized instructions to further accelerate the processing. So as you find, if you look at when it's processing, say using the AVX2 instructions, you're seeing that you get quite a good scaling across the processing, and there's a very good white paper that details all the information about the multi-buffer library at this link, and you can actually download, that's the download link then, just to the actual multi-buffer library, which is required to be downloaded and installed when you want to if you want to use this PMD. The QuickSys device is an Intel, the DX899X series that we've developed for Cledo Creek. This is the second PMD, and on that I've just highlighted it here in bold. The elements of that device supports symmetric, asymmetric, and data compression. But for this implementation, just the bolded out algos are the ones that we're supporting. And just the only other limitation, the way we use the Quick Assist, it still requires that you have the PF kernel driver installed, and what you do is get it enabled SRIOB devices, and then you've got 32 virtual devices that can be used within DPDK. So performance-wise, there's actually in the patch set there's in the test app in DPDK there's two tests that you can run, and basically you can run a QAT or the multi-buffer PMD, and they'll give you you'll be able to see the performance numbers for yourself on your particular platform. This is just showing, so on the lower is the increasing packet size and the throughput in gigabits per second. So I'm not allowed to give the numbers, but what you find is it's a very lightweight API because the performance team haven't looked at it this yet. But if you look at the white paper, the blue tracks practically identically the performance that's laid out in the multi-buffer white paper. There's little or no overhead, and the Quick Assist numbers pretty much matched exactly as expected in its documentation as well. So the actual library is very lightweight, but we haven't got to the official point where we can release numbers for future work. So we're looking possibly adding asymmetric crypto to the data path as well. That's we've only started looking at that and see really what the community need for it is. And then the second point we started looking at is developing an IPsec stack based on BSD kernel implementation. So we've got a very basic prototype of that working, which quite performance-wise is poor enough at the moment, and we've got a lot of ways we want to look at improving that, and hopefully we'll be able to release that to the community in the coming months. So that's it. Sorry, that was a whistle-stop tour. Yeah.
Yeah, thank you. So that's the second device API in DPDK, just after the ETH Dev one.
Yes.
Congratulations.
So at one point in that, I tried to reuse as much of the ETH Dev infrastructure as possible without replicating it. There probably is work that could be looked at in the future, that pulling out a core device type and making it more flexible, but it wasn't really in the scope of what we were trying to do, so I think that's future work.
I had a question.
Yeah.
So you chose to use the mbuf for this API, you chose to extend it?
Yeah.
But given that the cache line size is limited, what will happen to mbuf when we want to integrate new API, let's say for compression or video?
I suppose there's probably a number of things we could look at doing that. One would be you're probably only going to be submitting if it's an offload acceleration like crypto is. You could look at that, making that a union, and it's a single offload, or maybe we could have. There's a number of ways of approaching it. I haven't thought too strongly about a particular implementation because it really depends on what the next type of device offloads are and how we envisage that information needs to be passed through.
But do you think the mbuf should be the structure used for every API?
It makes sense for pipelining if the information is attached to the mbuf, as opposed to creating a new encapsulation and using that as to the device. I think it does make sense, and for something like crypto, which is a fairly computationally intensive task anyway, especially if you're doing it on core, the overhead, this hidden second cache line, is probably insignificant to what the processing you're going to be doing. If you're doing 600 cycles of processing on a crypto operation, I'm not sure that it's going to make a performance, but obviously we haven't tested that, so I can't commit to it.
But this transformation, or everything that you said, is not only related to crypto, so it could be any transformation like compression. So it will probably make sense to make this more generic and not.
Yeah, we certainly, I think at the mbuf level, we could make a much more generic structure. Instead of having it specific for crypto, you could have that slightly more of a generic offload, or absolutely maybe even go to the point where you're able to chain different offload types together, then use the transform the offload flags to dictate what types of offloads are available. That's certainly an option. And this is the first one, and I didn't see the point of doing that without some understanding of the other types of offloads that we want to do. I think as we look at what they may be, it'll give much more clarity on to how we should approach that.
All right.